Welcome to the Deep Dive, the place we turn dense, pivotal historical documents into essential knowledge. Today, we're diving into something pretty fundamental, the birth of wireless telegraphy.
And we're doing it through the eyes, or rather the words, of the main architect himself, Guglielmo Marconi.
Exactly. We have his 1909 Nobel Prize lecture, Wireless Telegraphic Communication. It's a fascinating first-hand account.
It really is. And what's great is it's not some polished hindsight is 2020 story.
Yeah.
He delivered this on December 11th, 1909, looking back over 15 years of intense work.
And he's remarkably frank. He admits right there in the lecture that his breakthroughs were often, to a great extent, the results of one another. It sounds like constant tinkering and building on what came just before.
Yeah, very iterative. And he even says, after spanning the Atlantic, that many facts connected with the transmission of electric waves over great distances still await a satisfactory explanation, even in 1909.
It's amazing. It shows how engineering and just sheer persistence can sometimes outpace the pure theory. So our mission today is to track that evolution.
Right. We want to pinpoint the key technical steps, look at the surprising scientific puzzles he ran into, and really get a sense of the effort it took to get from, well, a backyard experiment in Italy to global communication.
From a half a mile to crossing oceans, let's jump in. Okay, so let's set the scene. 1895. Marconi's background is kind of unusual for such a pivotal figure in physics and engineering.
It really is. He never went through the standard university physics or electrotechnics programs. He was largely self-educated.
But clearly very well read. He knew the work of Hertz, Branly, Ree, the big names in electromagnetic waves at the time.
Absolutely. He absorbed their published work, and he started his own experiments in 1895 at his family home near Bologna with a very practical goal in mind.
Not just exploring the science, but building something useful.
Exactly. He wanted to transmit telegraph signals using these Hertzian waves reliably over distance, without wires. The key word there is reliably.
Because the existing ways of signaling without wires, like using flashing lights or heliographs.
Totally unreliable. Fog, rain, hills, anything could block them. Marconi saw electric waves as a potential way through the atmosphere if he could just get the equipment to work consistently.
Which brings us to the first major roadblock, the detector, the receiver.
Right. He started with a standard setup, a Hertz oscillator, which is basically the spark gap that creates the waves, and a Branly coherer to detect them.
Explain the coherer again. It's kind of a weird device.
It is a bit strange, yeah. It's essentially a small tube, usually glass, filled loosely with metal filings. The idea is that normally the filings are a poor conductor.
Like a switch that's off.
Exactly. But when an electromagnetic wave hits the antenna connected to it, the tiny voltage is enough to make the filings, well, cohere, stick together just enough to conduct electricity.
The switch turns on.
Right. But the problem, as Marconi found immediately, was that the standard Branly coherer was, in his words, far too erratic and unreliable for practical work. Sometimes it worked, sometimes it didn't. Useless for telegraphy.
So job number one was fixing the detector. He had to build a better one himself.
He did. He experimented and landed on a much more stable design. His version used specific filings, nickel and silver packed into a very small gap between two fitted silver plugs, all sealed in an evacuated glass tube.
And this specific combination worked?
He claimed it was remarkably sensitive and reliable. That reliability was the absolute key to making any progress.
Okay, so now he has a reliable switch. How did that translate into receiving a Morse code message?
The improved coherer was hooked up in a circuit. When a radio wave closed the coherer switch, it allowed a small current from a voltaic cell, a simple battery, to flow.
And that small current wasn't enough to make a click itself, right?
No, but it was enough to activate a sensitive telegraph relay. Think of the relay as an amplifier. It uses the small current to switch on a bigger circuit.
And that bigger circuit could power
A chapper to make an audible click, and crucially, a recording instrument like a morph inker, which would mark a paper tape.
So a long burst of waves makes the coherer conduct for longer, keeps the relay closed, and makes a long dash on the tape. A short burst makes a dot.
Precisely. Morse code, received wirelessly and recorded automatically. It was a complete system, albeit a simple one.
And how far could this initial setup reach? We mentioned the power source was an ordinary Ruhmkorff coil. What is that, basically?
Think of it as an early transformer, really good at taking low-voltage DC from a battery and kicking it up to the very high voltage needed to make a spark jump across the oscillator's gap. Standard lab equipment for spark generation back then.
Got it. So with that coil powering the oscillator and his improved coherer at the receiver,
He managed to get signals reliably up to about half a mile, maybe 800 meters or so.
a decent start, but then he hit the next wall direction.
Right, the waves just went out everywhere. He tried focusing them using re-oscillators, which were designed to produce shorter waves, and putting them in front of parabolic reflectors like a headlight.
Did that work?
It did, in a way. It sent the signal in a specific direction, but only if there was the clear line of sight. He said it was immediately inoperative if hills or any large obstacle happened to intervene.
So back to the flashlight problem. Useful in clear weather on flat ground, useless otherwise. The waves in this setup were behaving exactly like light. Okay, so that line of sight limitation seemed fundamental. If the wave acts like light, the curve of the Earth or any big obstacle is going to stop it. This is where Marconi makes a leap that honestly seems counterintuitive.
It really does, especially against the backdrop of pure Hertzian wave theory. In August 1895, he tried what he called the new arrangement, and this is the absolute bedrock of his system.
Describe this new arrangement. What did he actually change?
It was surprisingly simple, yet profound. At the transmitter, instead of just having the two sides of the spark gap connected to plates or rods, he connected one terminal of the oscillator directly to the Earth.
Like hammered a stake in the ground.
Essentially, yes. A good electrical connection to the ground,
Oh.
and the other terminal of the oscillator he connected to a long wire or a metal plate, what he called a capacity area, hoisted high up in the air on a pole.
Okay, so one side grounded, the other side elevated. What about the receiver?
He mirrored the setup. One side of his improved coherer was connected to Earth, and the other side was connected to another elevated wire or capacity area.
Grounding both the sender and receiver and using elevated antennas. Why was this so radical?
Because it fundamentally changed the role of the Earth. It wasn't just the surface the equipment sat on anymore. It became an active part of the radiating and receiving system. He stated this combination of ground and height was the main feature of his invention.
And the results were immediate.
Dramatic. He started systematic tests right away, varying the height of the capacity areas and measuring the range, and he found a clear, powerful relationship.
He gives specific numbers in the lecture, right, using standard metal cubes.
Yes, he used cubes of tin, 30 centimeters on a side, as his elevated capacity areas. When the poles holding them were only 2 meters high, he got 30 meters distance.
Okay.
Raise the poles to 4 meters high, the range jumps to 100 meters. Not double, more than triple.
Interesting.
Raise them again to 8 meters high, and the range quadruples from the 4-meter mark, hitting 400 meters.
Wow, so the range wasn't just proportional to height, it was scaling much faster, almost like the square of the height?
Roughly, yes. It showed this deep interaction between the elevated conductor and the ground plane beneath it.
Oh,
And then he tried bigger capacity areas.
what happened then?
Using larger cubes, 100 centimeters on a side, still at that 8-meter height, the range suddenly leaped to 2,400 meters, nearly a mile and a half. And crucially, the signal went out all around, not just in one direction.
And this wasn't line of sight anymore. Could it go over hills?
That was the key discovery, it seemed to. Small hills or obstacles didn't stop it like they did with a reflector setup. The Earth connection seemed to help the waves somehow follow the terrain.
This must have gotten attention.
Oh, absolutely.
Yeah.
He took this system to England, and the British government ran tests. The ranges just kept climbing. September 1896, they hit 1 and 34 miles on Salisbury Plain. By March 1897, they reached 4 miles. And just 2 months later, May 1897, they successfully transmitted 9 miles across the Bristol Channel, all using that same basic principle, elevated aerial and Earth connection, powered by a relatively small Ruhmkorff coil.
9 miles is serious distance. But you mentioned earlier that the established physics community was skeptical. Why didn't they immediately see the importance of the Earth connection?
Well, it didn't fit their models. The pure Hertzian theory treated the waves as propagating freely in space, away from the ground. They tended to dismiss Marconi's results.
How? What was their explanation?
Some argued it was just brute force. Maybe his new coherer was just that much more sensitive, or maybe he was using way more power than he let on. They erroneously considered, as Marconi put it, the elevated wire and the Earth connection as sort of incidental, not fundamental to how the waves were traveling.
They missed the core innovation.
Many did, initially. But Marconi credits a couple of physicists who did get it early on. Professor Ascoli in Rome, and especially Professor Slaby in Germany, both writing in 1897.
What did they recognize?
They saw that the aerial and the Earth weren't just supports. They were integral parts of the oscillating system. The physical dimensions of the aerial Earth system were actually determining the wavelengths and how the energy was launched.
It was a completely different kind of radiator than Hertz's original dipole.
Exactly. And Marconi himself became absolutely convinced. He makes this really strong statement in the lecture. No practical system of wireless telegraphy exists where the instruments are not connected to Earth. Bold claim.
Did he mean a literal wire in the ground always?
He clarified that.
Yeah.
The connection didn't have to be a direct metallic conductor. You could achieve the same electrical effect using a large capacitor in series with the earth wire.
Why would a capacitor work? It blocks direct current.
But these are high-frequency alternating currents. Radio waves oscillate back and forth millions, sometimes billions of times per second. To such high frequencies, a large capacitor acts almost like a short circuit. It allows the oscillating current to flow through it via displacement current.
So electrically, it's still coupled to the earth potential.
Precisely. Or, he said, you could even use a large metal plate placed very close to the ground, acting as one plate of a capacitor, with the Earth itself being the other. The point was, the Earth had to be part of the circuit for long-range transmission.
And the proof kept mounting. The culmination of this phase was crossing the English Channel, right?
Yes, in March 1899. After successfully testing up to 40 miles, they set up stations in England and France and established communication across the channel. A major milestone, proving this wasn't just a short-range curiosity anymore. Geographic barriers were starting to fall.
Okay, crossing the channel is huge, but it immediately brings up the next big problem. If this technology works so well, what happens when lots of people start using it? Chaos, right?
Exactly. The early system, even with the Earth connection, was like shouting in a crowded room. The spark gap transmitter, that vertical wire discharging to Earth, was what physicists call a damped oscillator.
Let's break down damped oscillator. What does that mean electrically, and why was it bad for communication?
Think of hitting a drum cymbal really hard. You get a loud CR that contains a whole messy mix of frequencies, and the sound dies out very quickly. That dying out is the damping.
Okay.
Electrically, the spark discharge was similar. It released its energy in a sudden, powerful burst, creating waves across a very wide range of frequencies. And the oscillations died down almost immediately. Very inefficient. Very messy.
Like radio static almost, but generated on purpose?
Sort of, yeah. And the big problem was, because it sprayed energy across so many frequencies, a receiver tuned to one frequency could easily be triggered by a powerful damped transmission on a nearby frequency.
Interference. If you had two ships nearby, both trying to transmit.
Their signals would just jam each other. You couldn't have multiple simultaneous conversations. It wasn't selective. This is where syntony, or tuning, became absolutely critical.
Marconi started working on this around 1898.
Yes. He realized he needed two things. A way to make the transmitter send out a cleaner, more focused signal, like a pure musical note instead of a crash, and a way to make the receiver listen only for that specific note.
Let's start with the receiver side. How did he make it selective?
He introduced what he called indirect coupling, instead of connecting the coherer detector directly between the aerial and the Earth.
Which would pick up everything the aerial intercepted.
Right. He now connected the aerial and Earth to the primary coil of a special transformer, called an oscillation transformer or a high-frequency transformer.
Okay.
The coherer was then connected to the secondary coil of this transformer. And crucially, this secondary circuit also included a capacitor. The coil's inductance and the capacitor's capacitance were carefully chosen so that this secondary circuit would resonate or oscillate naturally at one specific frequency.
Like tuning a guitar string to a specific pitch.
Exactly like that. The transformer would only efficiently transfer energy from the primary aerial circuit to the secondary detector circuit if the incoming wave's frequency matched the natural resonant frequency of that tuned secondary circuit.
So it acts like a filter. It only listens for waves of the correct frequency.
Precisely. This allowed for selective tuning. You could, in theory, have multiple transmitters operating on different frequencies, and a receiver could tune in to just the one it wanted, ignoring the others.
But that only works if the transmitter is also sending out a clean signal, right? Not that messy, damped wave.
Correct. He had to tackle the transmitter side, too. Starting around early 1899, he focused on creating feebly damped oscillations wave trains that persisted for longer, more like that pure musical note.
How did he make the oscillations less damped? Less like a cymbal crash and more like a tuning fork?
He essentially made the aerial system a better energy storage device. He did two main things. First, he increased the capacitance of the aerial system, sometimes by adding more wires or by placing earth conductors near the elevated wires.
Making a bigger tank to hold the electrical energy?
Kind of, yeah. And second, he inserted inductance coils in series with the aerial wire. Inductance resists changes in current flow.
So more capacity to store energy and more inductance to slow down how quickly it could radiate away.
That's the core idea. Think of a swing. A short, light swing stops quickly, high damping. A long, heavy swing keeps going for ages, low damping. By adding capacity and inductance, he made the electrical oscillations persist for many cycles, creating a cleaner, narrower frequency band.
This sounds like it's getting quite sophisticated electrically.
It was. It culminated in his famous patent number 7777 of 1900, which described the complete syntonic system.
What were the key requirements of that patented system?
Two main things. One, you absolutely needed that inductive coupling at both the transmitter and receiver, linking the aerial earth part to a separate internal circuit containing inductance and capacitance.
Okay, the transformer setup.
And two, the natural period of electrical oscillation of the aerial earth circuit and the internal condenser circuit had to be tuned to be exactly the same. They had to be in resonance.
Everything had to be perfectly matched, like tuning multiple instruments to the same note.
Exactly. He does mention, very fairly, that Professor Ferdinand Braun in Germany was working along similar lines with tuned circuits independently around the same time. It was an idea whose time had come.
Let's revisit that acoustic analogy Marconi used because it makes it so clear.
It's a great analogy. He said tuning the receiver allows it to integrate the effect of comparatively feeble but properly timed electrical oscillations. Just like in acoustics, if you have two tuning forks tuned to the exact same pitch.
You strike one, and the other one, even a short distance away, will start vibrating too, right?
Yes, but a tuning fork of a slightly different pitch won't respond at all. The tuned receiver accumulates the energy from the correctly timed pushes of the incoming wave, ignoring the others.
It's the difference between a whisper that only the intended recipient hears versus the old system, which was like shouting for everyone.
A perfect way to put it.
Yeah.
And the practical result was multiplexing. He showed diagrams, figures 9 and 10 in the lecture, demonstrating how you could connect several transmitters, each tuned to a different frequency, to a single sending aerial.
And on the receiving end?
You could connect multiple tuned receivers to a single receiving aerial. Each receiver would only respond to the transmitter it was matched with. This solved the interference problem and paved the way for actual commercial wireless traffic.
Okay, so syntony solves the traffic jam problem. People can tune into specific signals, but there's still this massive physical barrier, the Earth itself. After the Channel crossing, wasn't the general scientific view still that long distances were impossible because the Earth curves?
Oh, absolutely. That was the prevailing wisdom.
Yeah.
Just like with light, the horizon was seen as a hard limit. The Earth would simply curve away from underneath a straight traveling radio wave.
People must have calculated how high antennas would need to be for, say, transatlantic communication based on line of sight.
They did, and the numbers were ridiculous. Marconi mentions the successful tests in 1901 between St. Catherine's Point on the Isle of Wight and the Lizard in Cornwall. They were 186 miles apart. For a straight-line signal to clear the Earth's curvature over that distance, the antennas at each end would have needed to be over 1,600 meters high. That's over 5,000 feet, a mile high.
And what height were his actual antennas for that test?
Under 100 meters, less than 330 feet.
So the waves couldn't have been traveling in a straight line. The math just didn't work. The established theory was fundamentally wrong for these distances.
Completely broken. It forced a major rethink. Physicists had been focusing almost entirely on what Marconi calls free Hertzian radiation through space waves, just flying through the air, independent of the ground.
But Marconi's key innovation was the Earth connection.
Exactly. And he began to realize that this Earth connection wasn't just helping launch the wave, it was introducing fundamentally different effects related to conduction. The Earth itself was playing an active role in guiding the wave.
Okay, explain the difference. How does a wave travel differently if it's conducted versus just radiated?
Think of radiation like throwing a stone across a pond. It flies through the air in an arc. Conduction, in this context, is more like the wave is attached to the surface and gliding along it.
So the Earth isn't an obstacle, it's the pathway.
That became the new thinking, largely driven by Marconi's results. Professor J. Fleming proposed a theory that the waves propagated as semi-loops of electric strain that essentially glide along the surface of the Earth.
Semi-loops, like arches connected to the ground?
Sort of. And for this gliding to happen, Fleming argued, there had to be corresponding movements of electrons within the conductive Earth directly underneath the wave. The Earth wasn't passive. It was part of the wave's structure and movement.
That sounds like a radical departure from the free space wave idea.
It was, and it was backed up mathematically by Professor Zenneck. Zenneck's calculations show that when an electromagnetic wave travels along a conducting surface like the Earth, its electric field lines actually tilt forward.
Tilt forward.
Because the lower ends of these lines of force are dragging slightly due to the electrical resistance of the conductor they're attached to. This forward tilt is what helps the wave hug the surface and bend around the curvature.
Wow. So the success of long-distance wireless depends critically on how good a conductor the Earth's surface is.
That's the massive implication. The better the conductivity of the surface the wave is gliding over, the less energy is lost to resistance and the farther the wave can travel.
This completely turns the old thinking on its head. No wonder established figures like Lord Rayleigh were surprised.
Yes, Rayleigh admitted in 1903 that Marconi's transatlantic success suggested a more decided bending or diffraction of the waves around the Earth than anyone had theoretically expected. The conduction theory explained why.
And this directly leads to the well-known observation about transmission over sea versus land, right?
Absolutely. Seawater, being salty, is a fairly good electrolyte, as Marconi puts it. It's a much better conductor than most types of land, especially dry soil or sand.
So the gliding is easier over the ocean. The wave loses less energy.
Exactly. The range is significantly greater over sea than over land for the same amount of power. Marconi provides a specific example to prove this conduction dependence.
What was the example?
A test conducted near Poole, in England, in 1902. They had a ship transmitting to a shore station. The signal strength was monitored as the ship moved. At one point, a 1-kilometer-wide spit of sandy land moved into the direct path between the ship and the shore station.
Just a kilometer of sand.
Just a kilometer.
Yeah.
And the signal strength received at the shore station dropped noticeably, perceptibly, as soon as that purely conducting sand intervened. It picked up again when the path was purely over water.
That's incredibly clear evidence. The sand was acting like a patch of high friction, slowing down and absorbing the wave's energy as it tried to glide over it. The ground is definitely not passive.
Not at all. The sea provides a relatively smooth, low-resistance highway for the waves to travel along, bending around the planet.
Okay, so the Earth connection and the conduction theory explain how waves could potentially bend around the Earth. With syntonies solving the interference issue, the path was clear, conceptually at least, for the biggest challenge yet, crossing the Atlantic.
Right. Around 1900, emboldened by the curvature results, Marconi decided to go for it. Europe to North America. About 4,000 kilometers, or roughly 2,500 miles.
That's a huge leap in distance. What did it require technologically? Just more power.
A lot more power and a way to handle it. The transmitter built at Poldhu in Cornwall, England, was a beast for its time. It operated at about 25 kilowatts.
25,000 watts. That's serious power for 1900. How did they radiate that effectively? Did they just build mile-high antennas?
No, interestingly, the Poldhu aerial wasn't exceptionally high, only about 48 meters or 160 feet. Instead of height, they went for massive capacity. They built this incredible structure, a fan-like arrangement of numerous bare copper wires suspended between masts, all converging down to the transmitter building. It looked like a giant conical cage. This huge surface area gave the aerial system the large electrical capacity needed to store and then radiate that 25 kilowatts of energy efficiently as a persistent, low-decrement wave.
So capacity over height for this extreme distance. And this setup led to the famous first signals.
It did. In December 1901, Marconi and his assistants were at a temporary receiving station set up on Signal Hill in St. John's, Newfoundland. They used a kite to lift the receiving aerial wire.
And they heard.
They detected faint, intermittent signals, specifically the Morse code letter S, 3 dots, being sent from Poldhu. It was highly controversial at first, very weak, hard to verify definitively.
So they needed more concrete proof?
Yes.
Yeah.
I came just a couple months later in February 1902. Marconi sailed west from England aboard the SS Philadelphia, equipped with sensitive receiving instruments.
And they listened for Poldhu's signals as they sailed away.
Exactly. And the results were undeniable. They received complete readable messages recorded on tape by the instruments up to a distance of 1,551 miles from Poldhu.
Wow. Over 1,500 miles of recorded messages.
And they could detect the simple test letters, like the S, even further out as far as 2,099 miles. That transatlantic voyage provided the conclusive proof that wireless could span the ocean.
That must have triggered a huge push towards commercial service.
It did. Marconi's company worked rapidly to build more powerful, permanent stations, notably one at Glace Bay, Nova Scotia, Canada. The first official messages between heads of state crossed the Atlantic via these stations on December 16, 1902.
And regular service followed.
There were intermittent press transmissions to the London Times in 1903, but establishing a fully reliable two-way commercial service took several more years of technical refinement. Regular public service finally began between Clifton in Ireland and Glace Bay in October 1907.
So transatlantic wireless becomes a reality, but this success immediately highlighted a really weird, unexpected problem, didn't it? Something first noticed on that Philadelphia trip.
Yes, the biggest, most persistent puzzle in long-distance radio, what Marconi calls a most important factor, the daylight effect.
What exactly did they observe?
It was stark. The range they could achieve at night was dramatically longer than the range they could achieve during the daytime. His estimate was usually more than double.
So sunlight somehow kills the signal strength, like a fog rolling in.
That's exactly the analogy he uses, later sunlight acting as a kind of fog for certain radio waves. It was a massive effect. Messages that were strong and clear at night would fade out completely during the day over the same distance.
What was the thinking in 1909 about why this happened? He mentions Arrhenius and J.J. Thomson.
Right. The prevailing hypothesis, which Marconi seemed to favor, was based on the relatively new discovery of the electron. Following Svante Arrhenius's ideas about ions in the atmosphere and J.J. Thomson's work showing that electrons absorb energy from electromagnetic waves passing through them. The theory was that sunlight itself, perhaps through ultraviolet radiation, was creating vast numbers of free electrons in the upper atmosphere. So the side of the Earth facing the sun would have this dense layer of electrons.
And that electron layer would absorb the radio waves trying to pass through or glide beneath it.
Exactly. The sunlit atmosphere becomes less transparent to electric waves, or as Fleming put it, a slightly turbid medium that dissipates the wave's energy. The dark side of the Earth, lacking this solar ionization, was much more transparent, allowing the waves to travel further.
That makes intuitive sense. A clear path at night, a foggy path during the day. But you mentioned a paradox about the wavelength.
Yes, this is where it gets really interesting and counterintuitive again. Marconi notes that his practical experience with the very long waves used for the transatlantic service, waves around 8,000 meters long, seemed to contradict some aspects of the theory, including work by Fleming. He found that these extremely long waves actually suffered less from the daylight effect than shorter waves. Sometimes he even observed that the signal strength received from these long waves during the day was stronger than at night, which is the complete opposite of the general rule.
So longer waves cut through the fog better? Or maybe travel differently?
It seemed that way. Whereas the shorter waves, like those used for typical ship-to-shore communication, say 600 meters, were very strongly affected. For them, sunlight was definitely a barrier. The effect was wavelength dependent in a complex way.
The atmosphere interacts differently with different sized waves. Wild.
And there were other timing anomalies too, right, around sunrise and sunset.
Yes, he describes a curious result observed daily at the Clifton and Glace Bay stations. These stations normally used a very long wavelength, around 14,700 feet, which is about 4,500 meters.
Okay.
But for a specific window of time each day, starting about 3 hours after sunset at Clifton, the transmitting station in Ireland, and ending about 3 hours before sunrise at Glace Bay, the receiving station in Canada, something odd happened. What?
During that specific 6-hour window, a shorter wavelength, around 12,500 feet, about 3,800 meters, would suddenly come in with remarkable strength, often overriding the longer wave they were meant to be using.
So for 6 hours, straddling the middle of the night path across the Atlantic, a different frequency became optimal.
Exactly. The operators actually learned to shift frequency during this period to maintain the best communication. The thinking was that this window corresponded to when the entire wave path between the two stations was in complete darkness, and perhaps some layer in the upper atmosphere formed a particularly efficient duct or waveguide for that slightly shorter wavelength.
It's like the atmosphere itself was tuning the transmission path. Incredible.
It really shows how much they were learning empirically by observing these strange daily patterns. He also mentions tests done on the Italian cruiser Carlo Alberto in 1902.
What did those show?
They sailed through the Mediterranean and into the Atlantic, receiving signals from Poldhu. They found that even large mountain ranges, like the Alps or the Pyrenees, lying directly in the path between them and Poldhu, did not significantly reduce the signal range at night. even using relatively short waves, around 1,000 feet or 300 meters.
The waves just sailed right over the mountains in the dark.
Apparently so, guided by the conductive nighttime atmosphere. But during the day, those same mountains drastically reduced the range.
Again, proving the atmospheric condition was far more important than the ground topography, especially for long distances.
Precisely. And finally, he touches on those brief periods right around sunrise and sunset when the signal path is transitioning from dark to light, or light to dark.
What happens then?
Signals often became very weak or faded out completely for short periods. He speculated that the sharp boundary between the illuminated and dark parts of the atmosphere might be reflecting or bending the waves away from their intended path, like hitting a refractive boundary. He noted this might be less of a problem for transmissions going north-south, staying within similar lighting conditions.
It's just a constant battle against this dynamic, invisible, and barely understood medium. So despite these atmospheric mysteries, the technology is advancing. By 1909, they're running commercial services. What were the big technological pushes in these later years covered by the lecture?
Two main goals drove development: improving efficiency and selectivity, especially against natural atmospheric spherics, and increasing the speed of transmission for commercial viability.
Makes sense. Static must have been a nightmare with those early detectors.
A huge problem. So one area of focus was antenna design, particularly for long distances. The simple vertical wire radiates omnidirectionally, which is wasteful if you're trying to reach one specific point thousands of miles away.
So they developed directional antennas.
Yes. After trying various configurations, Marconi describes the system they adopted for the transatlantic stations. It involved long, horizontal aerial wires laid out, pointing in the desired direction.
Horizontal, how does that create directionality?
The theory and practice showed that such an aerial tends to radiate most strongly off the end away from the transmitter building and its earth connection. It confines the main lobe of radiation more towards the horizon in that specific direction.
Like focusing the energy in a beam, somewhat?
Somewhat, yes. It wasn't perfectly focused like a modern satellite dish, but it significantly improved the signal strength in the target direction and reduced wasted energy going elsewhere. And importantly, the same antenna worked for receiving.
How so?
A receiving station using this kind of directional aerial would pick up signals most strongly when they arrived from the direction the aerial was pointing. This gave them a way to determine the bearing of a distant transmitter, a primitive form of radio direction finding, hugely important for maritime safety.
Okay, so better focus. What about the signal itself? They needed something cleaner than the old spark gaps, especially to cut through static.
Absolutely. This led to one of the most significant technical advances Marconi describes: the move towards generating continuous waves, or at least very lightly damped waves, using mechanical means. The goal was a signal that sounded like a pure musical note in the receiver headphones.
Easier to pick out from the crash and bang of lightning static?
Much easier. The key invention here was his high-speed rotating disc discharger.
That sounds complicated. How did it work?
Imagine 3 metal discs mounted on a shaft, spinning very rapidly. The middle disc is insulated, while the 2 outer discs are connected to the high-voltage supply feeding capacitors.
Okay.
The discharge of the spark doesn't just jump across a fixed gap. Instead, it jumps from the outer polar discs to studs or contacts on the edge of the fast-spinning central disc.
Why does the spinning matter?
2 things. First, the rapid movement helps to physically extinguish the spark very quickly after each discharge cycle begins. Second, the high speed ensures that the discharges happen extremely rapidly and regularly, thousands of times per second.
So instead of one big messy spark that dies out slowly, damped, you get thousands of tiny sharp sparks per second, each initiating a very brief oscillation.
Exactly. And the effect of adding all these tiny, rapidly repeating oscillations together is to create a nearly continuous wave train with a very, very low decrement. He mentions values as low as 0.02. Highly persistent, very pure frequency.
And the result in the headphones?
A high and clear musical note. This made it vastly easier for operators to distinguish the desired signal from the low-pitched clicks and grinders of atmospheric static. It also allowed for much sharper tuning resonance at the receiver.
Makes sense. And speaking of receivers, the old coherer was probably useless for these clean signals and high speeds.
Totally obsolete for serious work by this point. It was too insensitive, too slow, and still erratic. Marconi had developed and adopted his magnetic detector, or MAGI, as the standard.
How did the magnetic detector work? No filings involved?
No filings. It was based on a different physical principle: magnetic hysteresis. Basically, a moving band of iron wires passes through coils. One coil magnetizes the wire, another coil is connected to the headphones.
Okay.
Normally, the magnetism in the iron changes slowly as it moves. But when a high-frequency oscillation from the aerial passes through a third coil wrapped around the iron, it suddenly shakes up the magnetic domains in the iron, causing a rapid change in its magnetism.
And that rapid change induces a current in the headphone coil.
Precisely. It produces a click or a tone in the headphones corresponding to the incoming radio wave signal. It was much more stable, reliable, and sensitive than the coherer.
And fast enough for high-speed telegraphy.
Yes, it could be coupled with sensitive relays to operate high-speed ink recorders, allowing them to handle the increasing volume of commercial traffic across the Atlantic.
It's fascinating how the technology co-evolved transmitter, receiver, aerials. But Marconi makes an interesting point near the end about fundamental efficiency, doesn't he?
He does. It's a striking paradox.
Yeah.
Despite all these sophisticated advances that tuned circuits the rotating dischargers, he notes that when it comes to pure efficiency, measured as distance achieved per watt of power, actually radiated by the aerial.
Yes.
None of the complex arrangements using condensers and elaborate circuits were actually more efficient than his original simple setup from 1895. The plain vertical wire connected to an earth and discharging via a simple spark gap.
You're kidding. The basic antenna was the most efficient.
In terms of range per watt, apparently, yes. He quotes Professor Fleming confirming that this simple method could achieve communication over 100 miles using only about 8 watts of power in the aerial. Phenomenally efficient.
So why didn't they just stick with that?
Because while it was efficient, it couldn't handle high power levels effectively, and it produced those awful, damped, interference-causing waves. For reliable, selective, high-speed, high-power communication, the more complex systems were necessary, even if technically less efficient in that one narrow sense.
A classic engineering trade-off. And he finishes by reminding us just how unpredictable radio propagation still was, even in 1909.
Yes, he highlights the extreme variability they saw all the time, especially in maritime communication. Ships designed for a normal range of maybe 200 miles, using half a kilowatt of power, would sometimes inexplicably communicate over 1,200 miles.
Freak conditions.
Total freak conditions. And he gives that amazing anecdote about the SS Caronia in the Mediterranean in 1909.
Right, tell that one again. It's unbelievable.
A Caronia is sailing near Sicily, practically right next door to several Italian coastal radio stations. But for some reason, they could not make contact with these nearby stations. Try as they might, no connection. But at the same time, they had no difficulty whatsoever communicating clearly with Marconi stations way up in England and Holland.
Over 1,000 miles away, across Italy, the Alps, France.
Exactly. The signal somehow completely skipped over the local region and landed perfectly in Northern Europe. An atmospheric duct, maybe? Reflection off a high layer? Nobody knew for sure. It just highlighted how much was still unknown about the physics.
But despite the unknowns, the utility was undeniable.
Undeniable. He concludes by stating plainly that wireless was now a major necessity for the safety of ships at sea. It was connecting islands, linking colonial empires. He mentions the new Italian station at Coltano, aiming to reach East Africa and South America. The world was being wired, wirelessly. #tagged outro. So when you boil it all down, this whole revolution in communication wasn't just about one brilliant idea. It was really about, well, two key things Marconi drove home.
What are they?
First, that radical practical step of making the Earth itself part of the system, the Earth connection and the elevated aerial. That's what let the waves beat the horizon.
Right, the conduction idea.
And second, just relentless experimentation and adaptation. He kept hitting these weird phenomena like the daylight effect that the theories couldn't fully explain, but he found ways to engineer around them or even use them, like the operators changing frequency at night.
He didn't wait for the perfect theory. He built what worked. And he declares in the lecture quite confidently that wireless telegraphy has come to stay and will not only stay but continue to advance.
And he was absolutely right. It advanced because he trusted the experimental results, even when they flew in the face of accepted physics at the time.
Which leads us to his final thought in the lecture, a really provocative piece of speculation.
Yeah, it's pretty mind-bending. He muses about what might happen if these waves really can travel all the way around the Earth following its curvature.
What does he suggest?
He speculates that the electrical energy, after traveling 180 degrees around the globe, might actually start to reconverge, to focus at the point exactly opposite the transmitter, the antipodes.
Like waves focusing on the far side of a sphere?
Exactly. And if that were possible, he says, it might mean that someday you could send messages to the furthest possible point on Earth using only a very small amount of electrical energy, and therefore at a correspondingly small expense.
Wow. Hyper-efficient global communication by using the Earth itself as a giant focusing lens. Did that ever pan out?
Well, antipodal focusing effects are real, though complex and not quite as simple as he hoped. But the spirit of that speculation is powerful. It really makes you wonder, doesn't it?
How so?
It makes you think about technologies today. Maybe it's 6G wireless or deep space communication or quantum entanglement. What unexpected environmental factors or strange physical effects are limiting them right now?
Things we don't fully understand yet, just like the daylight effect back then.
Precisely. Is there some simple observable phenomenon, some practical trick like Marconi's Earth connection that we're currently overlooking because it doesn't quite fit our elegant theories? What's the next ground wire waiting to be discovered by observation?
A fantastic question to leave us with. Thank you for joining us for this deep dive into Marconi's world-changing journey, told through his own Nobel lecture.